Good evening, everybody. Um, Thanks so much, Mayuko, also for this possibility and for the organizers. Hi. Okay, let's see how this works. It's off. Okay. Hello? No, it's working. Yeah. I don't even know if it's really necessary to use it. I'll try. I'll try with it. Okay, yeah, you already know that today I'm going to talk about how we use actually artificial intelligence in the search for life outside the solar system. It's probably a bit more focused on the second part. I have to go to a lot actually to explain how we actually search for life beyond the solar system. So first of all, might be nice always. Let's see if that works. Mayuko, please go ahead. It's always nice to present my group. So as Mayuko has already said, I'm in Barcelona, exoplanet group led by my boss Ignasi Ribas. He earned a really huge grant a few years ago. So now this group really exploded, and we have a lot of people now working on this field, which is the detection and characterization of exoplanets. And especially, and that's what I'm also going to talk about a bit today, the problems we are facing these days in the search for planets. So there are two key words, of course. Maybe one of them is the reason why you are here. The worst is artificial intelligence. I will begin with this. I won't talk about robots. I won't talk about large language models. I will talk about actually neural networks, which are part of deep learning and machine learning and artificial intelligence, of course. Sorry. This may be a small overview of all those words which are going around. No, so artificial intelligence is actually very broad name. So no, you have really yeah, very broad. Machine learning is already a bit more specific. You have really what machines can learn. No, this is as well still very broad. You go down to deep learning. And the neural networks I'm going to talk about and also explain a bit how they work. And there are then different, say, architectures, how you can really put those neural networks together. And one of those advances then led to those large language model you all know about. I made this a few years ago. I'm sorry, I thought I had to show this. These are all the chatbots which are out there. I thought I'd look the countries where they are from, if they are really have, what ties they have and what they are doing. So you can see there are all not really good solutions. Yeah, choose your preferable choice, country and military and whatever. I'm using at the moment this Lejet from Mistral. Yeah, whatever, choose yourself. Okay. So this is probably one of the hardest slides I'm going to explain. So this is, I really want that you explain, that you know a bit how neural networks really work. So they are really just calculations, of course. No? So you have those neurons, there's one number coming in and there is one number going out. Here on the left side you see a bit the structure of this. I mean, with one number, those blue dots, you sum them up, you get to this orange dot, and then you form out of this a new number. No? And you do this by using 2 or 3 parameters you can actually adjust. And this is a whole mathematical system. So I always say that a neural network is practically an adjustment on all the input data you have at hand. So what your language models are doing is they are fitted to a huge amount of input data and produce then a probability of words from what they have learned before. No? And this is the most simplest architecture you can have. You have your input data and really go and calculate from one of those dots. One of those dots represents practically the whole thing on the left side. And you calculate from one number, the next number, going through this neural network and arrive at a specific number, which then you can adjust to the value you actually want to achieve with this. Yeah, you have to help me. I think. Yeah. Okay, now it goes already. It gets fast, very complicated. Here, it's not only that I calculate one number by another, but I can already scan little region of images, calculate of those little regions of images, new numbers, and then go again through my neural network to arrive at here at this case at the definition of what is this image actually representing, a number from 0 to 9. No? And the next image is a nice little video which then really shows what is happening at each of those layers, at each of those neurons. You can see there's a 0. It gets somehow processed through this neural network, calculating number. And here I always want the correct number to come out. No? So there is a mathematical procedure to really adjust all my input data on what I want as output data. This is practically a neural network. Architectures can get as complicated as they want, but it's always how it works. Okay.
What does this do?
The next thing is, of course, life beyond our solar system, and that's what I'm talking about in the next half an hour probably. So please go ahead. And I really wanted to begin with that you understand actually what light is from the view of a physicist. That's really important to understand, to later understand what we are doing there in exoplanet science. I think you can go twice already. Yes. Okay. Light is always produced if two electrical charges are moved one against each other. No, so we are dealing here with two strange concepts. This is an electrical field and a magnetic field. You heard of it, but you probably won't have a good understanding of it. No, and I can tell you probably nobody has. Those are just things we have in our world. Those are very famous formula found by Maxwell. And so it's always like this. If you have two of those charges moving one against each other, you will get some light out of it, depending on the charges and on the movement, on the velocity of those particles or of those charges. No. Depending on this, the light will have a different wavelength. So all what you can see here is the whole so-called electromagnetic spectra, ranging from those evil gamma rays and X-rays and even ultraviolet, down to the nice visible light, which is not at all strange that we are sensible there with our eyes, because the sun is shining there the most. Goes to infrared, microwaves, radio waves. So this is all the same thing, just with other wavelengths. No? And so what Maxwell found out, that it is actually by moving those charges one against each other, you create an electrical field. And then orthogonal to this field, a magnetic field is induced. No? And so you have practically electrical field, magnetical field, electrical field, and this going in one direction with the speed of light, depending on the velocity of the charges moving ones against each other. Okay? Okay? Understood? Then please. The next thing. Okay. So you know, of course, or you know, hopefully, that everything is made out of atoms. There are already charges in there. So everything is practically constantly moving against each other and producing light thereby. And you can see here, this is practically the distribution of the wavelength in the x-axis, or here from left to right. And from bottom to top, there is the intensity, and you can see here the distribution of light of whatever body with the temperature you see here at those curves. This is Kelvin. This is practically the same, say, as Celsius. So you have a different distribution of light according to the temperature of the body. So as you can see here, for example, our sun has a temperature of 6,000 Kelvin. Its maximum is exactly at the wavelength where our eyes are sensible or sensitive. So this is not that's the reason why we are sensitive there. So everybody also, many people always, for example, there are those famous images of auras of people. They are probably mostly infrared images of people because they also radiate. Everything radiates light, everybody. Okay. And then it goes further. So that's what I want to explain here. No? So from the light we can get information information of the temperature of the body. And then Fraunhofer, I'm not sure when actually, 140 years ago I think, analyzed the light of the sun and found those strange differences between this curve you just saw, no? And this was practically the birth of modern astronomy, because it's not only the temperature which we can find out, Mayuko, thanks. It is also the material which is actually emitting there, no? And here you can see nicely on the right side, this is just this part where our sun is emitting the most. And you can see here a nice classification of the stars we astronomers have made according to how this shape of the light they emit is distributed. And you can also see that there are different holes, so-called lines, which are produced by those different atoms or molecules are produced. No? So this you can see at whatever source here on Earth as well. You can really look what is hydrogen, what kind of light is hydrogen, and what kind of lines does it show. And so this is basic knowledge for us astronomers to really go further than in the analysis of the light coming from the stars. And this is, I think, a really nice image. Maybe you remember this from your chemistry class. How is it called in English? I don't. Well, periodic table of elements. Yeah. And you can really see that every element has its clear signature, no? And you can identify it clearly in wherever you look at. So I can now, and that's what I want to tell you, I can now identify the temperature of an object and what material there is at whatever distance. If I get light, the information is there. Okay? Please. Okay, then you can go forward in how to detect exoplanets. Please. This is also something I showed at the Institute from Mayuko. This is a star. If we zoom in, at some point you see this little pizza. This will be the whole solar system and the planets orbiting there. So you have actually at that star, this is Tau Ceti, no chance to see your little planet close to this super bright star. In that case, it's 10 billion times less bright. But we found some other indirect methods, no? And this I'm going to talk about. Please, Mayuko. 1995, this was the first detection, very famous, 51 Pegasi B. Those guys there, getting older from top to bottom, found the first exoplanet around a solar type star in 95. And they also got this Nobel Prize in 2019. Quite nice work. And they are also still leading this field in Geneva, where they are still located in, and have a big exoplanet group there. Please. So now maybe this is also a complicated but very important method to detect the exoplanets. This is the radial velocity. So how to explain this best? People always use this example of the ambulance, no? The difference of the sound the ambulance makes when the ambulance goes away and comes to you. You have
Doppler effect.
the Doppler effect. Yeah. So you have a change, an apparent change in the length of the wavelength, according to how you move to your source. Very easy to understand. It's the same if you would be in the sea and just walk with the wave, it would never change. And if you run towards the wave, it would hit you much harder and often. So that's the Doppler shift. And the Doppler shift is something I can only measure in this direction. No? And so as you can see here, at this one, this shall show you the spectra of the light. The lines you know from the laboratory are those dashed lines, and then through the movement of the planet, those lines, so the whole spectra gets moved around in for different longitudes. No? I forgot to explain, of course, as you see on the top left here, a misunderstanding always. It's not only that the planet is orbiting the star. No? It is that the planet and the star are orbiting the center of gravity of the system. So there is an actual movement of the star, and with this method we are able to move the radial component of this movement. And here you see then some nice measurements. If you just always look, how is this? Make it easy. How is you saw before that those spectra always have those lines. If I look at one line, this line will move around. If I always measure it, I can put something like this here, some nice curve in a plot. And here, this one is actually the detection for this 51 Pegasi V, this famous paper. So here you can clearly see that this is a detection, and there's no other possibility to have something that nicely distributed there. With this method, we are then, of course, able to measure how is the orbital period actually of this planet, how is its mass, very important, and what is the distance to its host star. Please. Here I have a small overview of what that actually would mean in our solar systems. You see the top line here, period in years, is how long it takes for those planets to orbit around the sun. This K thing is the influence this Doppler shift has actually on each of those planets. And I marked in colors, in green, the ones we would actually be able to detect these days. In yellow, it would be difficult, and in red, impossible. If it's this K value with K is in red, then it is just because this is lost in noise. And this one is, of course, because we are only now measuring maybe for 30 years exoplanets. So if an orbit is 80 years long, we don't see that, of course. This method is heavily biased in finding, of course, large planets, which are very close to their host star. This is also the kind of planets we were finding probably the first 10 years in exoplanet science. And then there is this other method, or a bit more obvious actually. Here we make photos, just photos every 10 seconds, and look how bright the star is. And at some point, when we are lucky, there will be a planet crossing the surface of that star, and we will have such a small dip. Actually, we are very much into the details of this small dip these days, but still, this is one of the best methods actually to detect exoplanet. We have satellites in space which can observe thousands and thousands of planets at once. Same problem here. The larger the planet and the closer to their host star, the better we can actually find this. I also want to stress here this dependency, this little formula here as well. This will be important in a minute. So this depth of this so-called transit depends on the radius on the radius of the planet. No? So you can see that. No, you don't see that here. Here the star is a bit different. No. But if the planet is bigger, then you have, of course, have a transit which is more deeper. No, okay. So those are small statistics of the planets we have found so far. There are those 30% of the gas giants, similar as Jupiter and Saturn in our solar system. We have already found, or 4% of the planets we have found are actually terrestrial, so they are similar as Earth. 35% are similar to Neptune and Uranus. And then there is this strange type of planets where we have found, where 30% of the planets we have found are those super Earth. So they are a bit in between Earth-like planets and those Neptune-like planets, and we are often not really sure if they are of this rocky nature or of this more gaseous nature. No, 6,300 planets we have found so far. Please. Okay, and this is also a very nice statistic we already have made. You know, of course, we have those 8 planets in our system. And they have those two, like I said before, those two distinct characteristics. We have those Earth-like rocky ones, and we have those huge ones which are practically just gas getting denser. So they are very, very different. Statistics already say that every star has more or less at least one planet in average. And that every second star has, in average, a rocky planet. So this is a huge number. We have about 100 billion stars in our galaxy. So there should be around 50 billion Earth-like planets in the galaxy. Okay. That's not, of course, not enough. The planets not only have to be rocky and small. It also depends a lot how close they are to their host star, of course. And here what we are doing is we calculate a zone where we assume that water could be actually liquid around this or on this planet. No? So you know the system or the elements we have, and life on Earth is carbon based, and for this we need actually water as a how is it called? Solvent, yeah, as a solvent. No, so that's what we are doing. Depends, of course, on what star and how hot this star is actually, and so the so-called habitable zone gets closer and closer to the star, the smaller the star is. Please. This from 2024. I hope this is still is this still okay? I think so, no? Those are the 29 potentially habitable worlds we have found so far. This means Earth-like and in the habitable zone. So those are our best objects so far, that there might be some similar life as we know. Most of them actually we already investigated a lot, and it's rather a bit difficult. And you see on the top left there is Proxima Centauri b. This is actually a planet around the closest star to the sun. So if we have any chance to go somewhere, this is a good place. Okay. Okay, so now we know a planet has to be rocky, it's habitable. Now we have to look further. How can we actually look for signs? Please. And there is this method developed also by Sarah Seeger. This is called transmission spectra. So I will get in detail in a minute. But in the moment a planet transits in front of the surface of its star, of course, part of its light also passes through its atmosphere, no? And as I said before, if light go through whatever other atoms or materials, it will be affected, and you will get different lines. Some light will stay at this atmosphere, some light will get through. Please. And here I have something interesting. So what we are, it's now getting already a bit more scientific. These are real observations of such a transit on the left side. And as I told you before, if you look at this little formula, the depth of this transit depends on the radius of this planet. So, and you can see that this is one star and one transit, but just in different wavelengths. And you can see that the depth is actually changing here. Okay. And this is what is happening here on the left side. Some of the light will actually be blocked maybe by clouds. Some light will go through, and some light will be actually interacting with molecules in the atmosphere. So this you will have again a quite clear analysis of what is happening of the with the light from the star when it passes through the atmosphere. And if you go wavelength by wavelength, you can actually construct something like this. This looks again a bit like one of those spectra I showed you before, and I can see here what is exactly happening with what wavelength when the light from the star goes through the atmosphere. And then I can again identify what is this wavelength actually connected to which molecule, to which atom. So I can really scan through the atmosphere and see what molecules are there. Okay? And then we come to astrobiology. This, by the way, a really beautiful image, I think. I think the comparison is always with an apple, no? That the skin of an apple is as thick as the atmosphere of a planet. So this is really, really, really small what we are here actually measuring. Okay. This would be the most obvious assumption. No? What do we need in an atmosphere? What molecules do we actually want to see in an atmosphere to say that there is life? Obvious ones are water, oxygen, carbon dioxide. We also have methane, for example. So this is something we would search for. Please. This is real data now, and you can see here what we are able to do at the moment. You see those dots, which are the measurements, and you can see those little lines, which are the uncertainties, which we always have to include as physicists in whatever data we have. And then we have our best fit model. So what molecules can explain that? We know exactly what water is doing, and this is a good fit. If this is really a sign that there is water, you tell me. But this is the best we have at the moment for this case, no? Please. And now we are coming, like the connection to the neural network will come soon. So this is like our techniques we have to find exoplanets, no? But these days, yeah, please, it's okay. These days our instruments are so incredibly precise. Like for this radial velocity, for example, for this movement of the spectral wavelength due to the movement of the planet around the star, we have precisions now which are in velocities of 1 meter per second. No? This is less than you can walk. So I can measure the movement of a star of velocities lesser than you walk. And then you look at the surface of the sun. Those are, or not all of them, but some of them are actual observations from the sun. And don't worry, some of them are really moving. And it's of course then really difficult to imagine that you can really measure down to that precision if you look at the sun already and see things like granulation, where you have hot material coming from the interior to the surface and falling down in those little nice cells. The whole thing, as everybody is oscillating, you see in the next picture here. We have magnetic cycles. Maybe you know that from the sun as well. Every 11 years, there are those nice spots which look a bit like this eye from Sauron, I think. And in the sun, no, there is a huge number, and then it increases in number and goes down to the equator, and it's like an oscillation as well. No, so this is called a magnetic cycle. The rotation, of course, influences as well. You always see something different. And if you now imagine, please, I think this you have to start somewhere. Yeah, you see, again, maybe you will see here a planet crossing. So imagine now you make a photo of this thing every 10 seconds that I said before, and you want to see that the light is dropping here because of that little dot. And this is happening on the surface. So this is now our problem at the moment. Please. Yeah, this maybe goes a bit too far. Here you see one of those lines and how they are actually influenced by a planet, where, as I said, it's just moving around from left to right very nicely. The wavelength is changing due to this Doppler shift. And then you have here one of those spots which is passing on the stellar surface due to the rotation. And you can see that there's something quite similar happening, but it's not actually really moving. But for us, as we measure here this movement, this is a huge problem. It's actually the same effect, and it's not really distinguishable one from another. Okay. And that is a bit my point, where I will now include the neural networks as well. So this is the bottleneck we have. We have this stellar magnetic effects. They are connected somehow and very complex with our exoplanet observables. So we have to find a way how to actually deal with those effects, and really to find only the effects the planets induce here. Please. Okay, then I think the next image is fun. I searched the internet for images of cats who look like dogs and dogs who look like cats. Yeah.
Did a good job.
Yeah, you know. But the question is here, actually, would you be able to write down a definition of what is a cat and a dog in this context? Would be quite difficult, I think. Please, the next. But I'm sure you could identify everyone. So this is the advantage a neural network has. So we as physicists, or probably also as humanity, we always want to really understand the connections. But actually, we are often just like a trained neural network, and we know the connections without really being able to name them. No? And this is what we are doing now. Not 100% happy with this, of course. We want the physical explanation, but it's too complex at this moment. And so we are really trying to, let's say, throw a lot of data, a lot of physics we already know at our problem. And with the solution a neural network can find, then try to really go deeper and try to understand why this is actually found. No? So this is what I'm saying here. And this connection which I make here with the dogs and cats is then the same, actually, of course, please, yeah, the same again with the one I've just showed you, please. And here the artificial intelligence and the neural networks come in. So as I said before, no, and this is quite important here. Our knowledge yeah, we won't get really the explanation we want to have, but we can really go after the solution and then analyze what we can learn out of this. Okay. I think you can, yeah, or the last, no, this one was with the more complicated architecture. Where was this? This. Yeah, this is just the last image. This is an architecture we have built with a student of mine. It looks a bit more complicated, as I said before. We are putting in here observables, modeled observables. So we have a huge code where we put all our physics in and train these neural networks with those or synthetic or modeled observables with a modeled output, train it as good as we can, and then hope that by putting real data in, we can really find the solution for our problem. Okay. You know this image? Oh, you should know. If you are here, you should know this image.
Voyager.
Yeah, Voyager. Who said that? Yeah. Great, thank you. This is the image from Voyager, made back to Earth, and you see this little dot here. This is Earth from far away. And from there, I say you the last slide, please. Thanks for your attention. So, okay, thank you. So, yeah, if you have any questions, or I don't know how the procedure is.
Yes, do you have any questions?
Please.
For your neural network.
Yes.
Sorry.
It was little on neural networks. I know.
For your neural network, what exactly are your inputs and what are your outputs?
We model those observables. No?
So you're guessing one of the observables from the rest of them?
Yes, there are observables which are only affected actually by this so-called stellar activity, by the effects the star is introducing. So I use all those and calibrate it with output data which is affected by both in the real observations. So I calibrate my only affected by the star data with what this would affect on data which normally is also affected by the planet. The idea is then having this neural network trained that I later can subtract the output of my neural network from the real data, and so I only have the planets left. So I simulate the contribution of the star to my observed data, where I also expect the planet information to be. Yeah?
Understood.
Is it possible to verify that information that you get from this system?
No.
You verify
Never.
it? No.
We can fly there. No. Mathematics, no?
Right, okay.
Yeah. But I mean, it's quite convincing, no? Looking at those lines, and you see really nice curves. Sometimes it's a bit more tricky, but yeah.
I was thinking that you built this system and the output that you get.
Yeah. You mean you?
The AI is suggesting.
Yeah. You mean the
certain
AI?
output, but can you verify that output?
I
At
mean,
the moment?
yeah. I mean, the system or you talk about the neural network only, no? Yeah. I mean, the neural network itself works perfectly. Only made with this modeled data, it works just perfectly. So if we now try it on real observed data, it has huge problems because our models are still lacking a lot of physics. Yeah. And as I said before, if I now train my neural network on data nobody can find a planet on and tell them there is this planet, nobody will believe me probably.
Right, okay.
Yeah. So it's we have to be as physicists really careful also to use this tool, I think. Yeah. So, but as I said, we can learn a lot about how things work about this, and also improve our models due to that. Yeah. please.
So how much of this is the physics, and how much of this is the artificial intelligence part that we're kind of like blinding ourselves?
No, it is completely based on those models, of course.
So it's
And those are complete physics, yeah.
physics based,
Physics
goes
based,
in,
data driven.
and then the
yeah.
data is, or the data is based on the neural networks.
No, the neural networks is a huge machine with billions of parameters to fit input data to output data.
Okay.
So I mean, I know you're from the field. I'm fitting the time series of my observations, whatever activity indicators I have, to the radio velocities.
Okay. I see. Thank you.
And this I do with a million models I created with as good as physics I can imagine. Yeah.
Yes. Go ahead. This is just for recording.
Thanks for the nice talk. Can you elaborate a bit more and on how, from the few detections or the 7,000 exoplanet detections we have so far, how you extrapolate to a number to claim that 90% of all planets in the galaxy must have
when we
planets?
don't detect the thing, we can also learn a lot about it. Non-detection is also something.
But if you don't detect a planet, how do you know that there is no planet?
We
or
have
you
limits. We have limits to see, and we also know what we can detect. No, I understand your. It's still a statistic thing, no? We have little rocky planets. You are right, 300 or something like this. And now I say that every second in the universe has such a planet, no? But it's statistics and calculations we can make of what we actually can see on the stars and what we can't. So of course you are right. Imagine that we live in a special place where there are more rocky planets than anywhere else. Then we are completely off. But that seems
all the
unlikely.
observation bias is
This is
accounted
all
for
taken care of course. Yeah.
Okay.
So we assume, of course, it's everywhere the same. That's for sure.
Okay, thanks.
Yeah.
Okay. One or two questions.
And it's also not this number plus minus 0 point. It's like uncertainty is there, of course. Yeah.
I have a question about the life that may or may not be out in the universes and the planets that the system is finding. All of what we're looking for seems to be based on Earth's definition of life.
Yeah.
What we see as living. Would it be possible that we miss alien life forms because we are deliberately not looking past our own parameters of what life is?
Yeah, cool question, of course. No, 1,000 answers I have. To begin with, if we make it so broad, we could not even look for something. No, yeah. Should it be connected to material? If so, then there are not so many possibilities anymore. Life on Earth is based on carbon. This is famously for connections and can build those large molecules. There are only few of them in the periodic table, and carbon is by far the most abundant. So it makes a lot of sense. And then you have also this solvent, which is water. I think there are calculations and ideas that life could also be made out of silicon, but it's much rarer, no? But this would be also able to form those long acids, amino acids, and so on. But it's you are completely right, no? But it would not make sense to search for other things. And maybe this is also something I actually not really said. We thought a few years that we actually can really find good biomarkers saying that if those elements or those molecules are in the atmosphere, then there is life. And in the last years, it seems rather that it is quite difficult to say that actually. So there are mostly for all of those appearances of molecules, also other possibilities. So this is also a huge field where I'm not the biggest expert, but very difficult, of course. What do you need in an atmosphere actually to see life, even on Earth?
A follow-up question, if you don't mind.
No,
Do you think that maybe our own periodic table of elements is maybe missing things that we can find on other planets?
no. I don't think. It's I think this is, well,
Pretty much what it's set to be.
if it's not like this, then many things should be wrong what we are doing, no? And we have so many things right. I mean, it's, if you look into physics in general, there are so many details where you see, this guy 200 years ago was right because now I can see this little thing here, no? So we know a lot, I think, about what is going on in the universe. But yeah, I share your doubts, absolutely. Yeah, but it's also not possible really to go there, no? Like, yeah,
Thank you.
yeah.
Okay, the last question.
Yeah,
Yes.
this is okay. Thank you so much for the very interesting talk. I think you mentioned in the beginning when you were talking about light and our sun, that the eyes of human are pretty adjusted to what is the light, etc., to the range of that. I'm not sure if I understand it correctly, but I want just to confirm. And does this statement include also other animals or other living being on our planet? Because sometimes you hear some have some kind of sensors to even sense other type of waves. I just wanted to learn a bit more about that.
This was really my point, actually. That maybe, yeah, this was absolutely my point. So our eyes are not sensitive to the light. We are sensitive to certain wavelengths of the light. This is all light. Radio wavelength is light. It's exactly the same. X-rays are exactly the same. And we humans are sensitive to the light where the sun is emitting the most.
Oh, okay.
Yeah.
Yeah, I think this thing.
Yes, and yes, of course, I know nothing about it, no. But doesn't a cat see better at night?
I have no idea.
And what else is there? An owl? Huh? Deep sea creatures, of course.
Because I heard
Yeah,
some
well-
animals are sensitive to electromagnetic waves.
This is light.
This is light.
Electromagnetic
Even
waves.
Stone sense, I don't know.
Wait. Electromagnetic waves is light.
Yes, of course, light, but to this wavelength. So we're using this as orientation, or somehow, so humans don't have this level of.
Yeah, as I said, I'm sure there are animals which are sensitive to other wavelengths, slightly at least, not to X-rays, for example. Yes. Okay.
Okay, so maybe if you have further discussion, sorry, please thank you.
Yeah, thank you.